Okay, in this video, I think I will be going through bonding and structure, which is topic 3C in our syllabus of Edexcel IAL. So I'll be going through basically the shapes of molecules. Okay, let's start. So before we actually discuss all the shapes of molecules, we have to go through the electron pair repulsion theory. So this is also called valence shell electron pair repulsion, because we have those electron pairs interacting in the very outer shell. The shape of the molecule is determined by the repulsion between the bonding and lone pairs of electrons that surround the central atom. So the important bit over here is the central atom. Depending on the central atom, we're looking at the shape of the molecule. The pairs arrange themselves so that the distance separation is maximum to minimize repulsion. So when you have magnets and you are putting them together, they repel strongly. However, if you go a little bit further away, they repel weakly. So that's basically what this revolves around. And the relative strength of the repulsions will be the lone pair and lone pair electrons repelling a lot stronger. Then we have the lone and bond pair, and then we have the bond pair repelling the weakest. So let's go on to the next slide. And before we actually look at the shapes of molecules, one more thing. We have the bond length and the bond angle. So we need to know the definitions of them. So the bond length is the distance between the two nuclei connected by a covalent bond. So when we're talking about bond length, really, we're predominantly just talking about covalent bonds. And we have the bond angle. It's the angle between two covalent bonds originating from the same central atom. Yeah, so we will be applying these stuff, the electron repulsion theory and the bond length and bond angle, into our shapes of molecules. So 3.18. With the principles in mind, we must be able to explain the shapes of molecules. You must include, when you're explaining the shapes of molecules, the number of bonds and lone pairs, so bond pairs and lone pairs, around the central atom, and that they're basically they arrange themselves so that the separation is maximum and they have minimum repulsion. And the relative strength of the repulsions between the electron pairs must be mentioned if there are different kinds. So let's look at examples now. So the first is a nice and easy example. This is a beryllium chloride molecule. So there are two bond pairs, as you can see, overlapping as the beryllium is a central atom. They arrange themselves so that there is maximum separation and minimum repulsion. And yeah, so the bond pairs over here is at maximum separation, making the bond angle to be 180 degrees. And when we have two bond pairs repelling equally, it gives a linear molecule when the bond angle is 180 degrees. Okay, so the next example, we have carbon dioxide. Now this time, we have 4 bond pairs, but 2 bond pairs form one electron dense area each. So there are 2 bond pairs here and 2 bond pairs here. So they're acting as one electron dense area and one electron dense area. So they arrange themselves so that there is maximum separation and minimum repulsion again. And obviously, if there are 2 electron dense areas, just like beryllium like this, it's going to be separated by 180 degrees and therefore result in a linear shape. And this time we're looking at a methane molecule. Over here, our central atom is carbon, so we have 4 bond pairs around the central atom, arranging themselves so that there is maximum separation and minimum repulsion. And if you look at this, we only have 4 bond pairs, which is all the same electron pairs, right? So they're going to just repel equally and be separated by 109.5 degrees. And therefore, it's going to result in a tetrahedral molecule. And the different example over here, we have boron trichloride. So this one has 3 bond pairs arranging themselves so that there is maximum separation and minimum repulsion. So we can see the 3 bond pairs around boron, and they're going to be repelling at equal amounts, giving a trigonal planar molecule with a bond angle of 120 degrees. You just divide 360 by 3, right? Yeah, this is a planar molecule because it's flat, and it's called trigonal because it has 3 points. As you can see, we have 3 points, the chlorines. Yeah, so that name, trigonal planar, makes sense. This time we have ethene. So over here, we have many molecules. Many atoms bonded together. But over here, we're going to count the carbon, one of the carbon atom as our central atom. So around one central carbon atom, we have 4 bond pairs. So we have one over here with hydrogen, another one with hydrogen. We have 2 between carbon because ethene has a double bond. So 2 of them make up 1 electron density, these guys, and the other two make 1 electron dense area each, right? So they're going to be separated so that they have maximum separation and minimum repulsion. So we have 3 electron dense areas, just like boron trichloride. Therefore, it's going to be having a trigonal planar shape. Or just around the central carbon atom. So obviously the bond angle will be 120 degrees. So yeah, ethene also is a flat molecule, therefore. Right. Oops, where am I going? Yeah, over here, just to make understanding the shape of and the bond angle of ethene a little bit easier. If you isolate one of the carbon atoms, it would look like this. So we have 3 electron dense areas being separated equally. So there are 3 electron dense areas around the carbon atom, therefore giving a trigonal planar shape. So we're going to look at ammonia this time, where we also have 1 lone pair along with 3 bond pairs surrounding the central nitrogen atom. So again, you have to mention the maximum separation and minimum repulsion between the bond pairs, and that right now lone pair and the bond pair repulsion is a little bit stronger than the bond pair repulsion. So because we have so when there are different kinds of repulsion around the central atom, you must mention the relative strengths of the repulsions. Okay, so over here, as you can see, we have lone pair, and the bond pair. Their strength of repulsion is going to be different. That's why over here you have to mention something else as well. In addition to how many lone pairs and bond pairs we have, and maximum separation and minimum repulsion. So over here, obviously, because the lone pair and bond pair is going to be separated by a larger bond angle, the bond angle over here between the bonds is going to be 107 degrees, okay? The lone pair is not a bond, right? So we can't really get the bond angle between the bond pair and the lone pair. So we're just going to look at the angle between the bonds, okay? So this is a trigonal pyramidal shape. So I drew a little diagram of a trigonal pyramidal shape like here. It looks like a pyramid basically with a 3-point base. So that's why it's called a trigonal pyramidal shape. Yeah, so next we have an ammonium ion. So this guy has 4 bond pairs that arrange themselves so that there is maximum separation and minimum repulsion. Over here, we know that ammonium ions are made up of a NH3 and a proton, right? So therefore, it's going to have a little positive charge. And because this has 4 bond pairs, just like methane, methane was this guy. With 4 bond pairs around the carbon atom, which had 109.5 degrees. Its structure is basically identical, right? So this is going to be a tetrahedral molecule. Just note that this structure has dative covalent bonding over here because nitrogen's lone pair is being added to the proton's empty orbital. So over here we have water. This time we have 2 lone pairs and 2 bond pairs. So they're going to go so that their separation is at maximum, and therefore they have minimum repulsion. But over here now we have 3 different repulsions, right? So we want to mention all the relative strengths. So the lone pair repulsion is going to be the strongest, lone pair bond pair repulsion is going to be the weaker, and bond pair repulsion is going to be the weakest. So over here, these bond pairs are going to repel very, very strongly. These guys don't repel as strongly, and these guys repel the least strongly. So they're going to have a smaller bond angle, which is 104.5 degrees. So that is our water molecule. Let's go to the next slide. Now we're going to discuss the bigger molecules. We have phosphorus pentachloride. Over here we have PCl5. Over here we have 5 bond pairs, and obviously they're again going to be arranged so that they have maximum separation and minimum repulsion. And it has 2 bond angles in this case. So we will have a P as a central atom, and then we have a little axis going through the P, and there's going to be a planar structure right in the middle. So basically, if I have a plane like this, there's over here we have the triangle, and then it's going through. So we have now a trigonal planar over here, and then just a linear going through that trigonal planar. So between that plane and that line going through, obviously it's going to be 90 degrees, as you can see over here, that's 90 degrees. And we have on the trigonal planar, the triangle there, we have the bond angle as 120 degrees. So and this shape is basically called the trigonal bipyramidal because now we have 2 pyramids on the top and on the bottom, right? So it's a bipyramidal, and it has a 3-point base, right? So it looks kind of like this. I tried to draw it. I'm not sure if you can figure out properly. Anyways, and also if you can see the phosphorus pentachloride over here, when we draw the just conventional dot and cross diagrams, we can notice that this one is a little bit different. It has 5 bond pairs on the P, meaning that phosphorus, pentachloride phosphorus has 10 electrons on its outer shell. How does it do that? So this is called the expansion of the octet. So this is by occupying empty d orbitals, so the 3 d orbitals that are empty. So electrons are promoted from the lower energy levels so that it can make more bond pairs. Okay, so that's expansion of the octet, so it can do that by occupying the empty d orbitals, electron promotion. Okay, so we have sulfur hexafluoride again. This one has 6 bond pairs, so they're going to be arranged so that they have maximum separation again and minimum repulsion. This is also an example of an expansion of octet, occupying the free d orbitals, right? And we have the molecules drawn over here. This over here now, it's kind of similar to our phosphorus pentachloride. Basically, we have a base and an axis going through again, but that base is going to be a square base. So it's going to have 90-degree bond angles only. So as you go, when the axis is going down on a plane, obviously that is going to be our 90 degrees. And then 4 points are separated on a plane like that. So if you draw axes like this, then it has a 90 degree, right? Just as you can see over here on the diagram. And so, yeah, that structure is called octahedral. As you can see, I tried to draw it again. And if I actually draw the base, kind of like that, can you see? This is going to be our 90-degree angle, right? And as you go through like this, we're going to have a 90-degree angle like that as well. Yeah, so that is our sulfur hexafluoride. So we also have to be able to apply these concepts to other molecules and ions. So you might see something very unfamiliar, but you just have to see how many bond pairs there are, how many lone pairs there are, and which one it looks similar to from what we have previously looked at. So this is a H3O plus ion. So this one actually forms from water joining with a proton, so water is kind of acting like a base, making an H3O plus molecule. So over here we have the dative covalent bonding. Okay, so that is our H3O plus ion. So there is one lone pair and 3 bond pairs. This looks like ammonia, right? So again, just mention that they are going to have maximum separation and minimum repulsion. And because there are 2 different repulsions over here, we have lone pair, bond pair repulsion, and bond pair repulsion, right? And bond pair repulsion is a weaker repulsion. And yeah, so which shape did ammonia have? It had a trigonal pyramidal shape, right? So therefore, H3O plus ion is also going to have a trigonal pyramidal shape with the same bond angle, 107 degrees. And let's look at 2 more examples. So we have AlCl3. Over here we have the aluminum on the central atom and it has 3 bond pairs around it. They're going to be arranged so that they have maximum separation and minimum repulsion. And because it has 3 bond pairs, what does it look like? It looks like kind of boron trichloride. And was it boron? No, yeah, it was boron trichloride. Yeah, so and also an ethene molecule where the central atom is carbon. Yeah, so we have the trigonal planar molecule with a bond angle of 120 degrees, just like the other trigonal planar molecules. And over here we have a pH3 molecule, which is a trigonal pyramidal shape, again, just like ammonia and just like H3O plus ions, because it has 1 lone pair and 3 bond pairs. So again, they're going to be arranged so that there is maximum separation and minimum repulsion, and there is going to be 2 repulsions over here, lone pair bond pair repulsion and bond pair repulsion, where lone pair bond pair repulsion is a little bit stronger than the bond pair repulsion. So yeah, these are some unfamiliar molecules, but we can just apply the number of lone pair and bond pairs we see and what the relative strengths are, and that they arrange themselves so that they go to the maximum separation and minimum repulsion. We can work out the shape and the bond angles. And this is, so just mentioning that is just explaining why they have that shape. Okay, so that is all for this session, and thank you for listening. See you in the next session.